Welcome everyone. Today's presentation on water resource engineering. Myself Sai Krishna. Now we are going to see about water power engineering of Unit 5 for final year students of Civil Engineering Department of the year final year students, first semester. So far we have completed. Let's see what are the topics in water power engineering. We have seen some introduction of it and we have seen types of water power developments. And also we have covered some classification of hydroelectric schemes. Proceedingly, we have seen some principal components of hydroelectric schemes and we have seen each and every topic detail. Namely forebay, intake structure, penstocks, surge tanks, turbines, selection of suitable type of turbine, powerhouse, and scroll casing, draft tube, and also we have seen about tail race. Okay. Now let's see what are the assessment of water power potentials. Today's our topic is assessment of water power potential. In this topic, let's see discharge in cubic meter per second, QMAX, height of fall in meters, discharge in QMAX, height of fall in meter. Then the rate of work done is QWH, that is equal to 9.81 into QH. W is nothing but gravity, 9.81 into discharge into height of fall. That comes in kilonewton meter or kilowatt. 1 kilonewton meter is equal to 1 kilowatt. Okay. Let eta ART be the efficiency of turbines and eta G be the efficiency of generators, and eta is equal to eta F into eta G, where B the overall efficiency. The electrical energy of power P generated by hydroelectric power plant is given by, that is P is equal to 9.81 eta T eta G QH. QH is nothing but discharge and height of fall, that is 9.81 eta QH kilowatt. We get finally 7.84 discharge height of fall, approximately 8 kilowatt. For usual values of efficiencies, the electric power available can be roughly estimated to 7.5 QH to 8.5 QH kilowatts. Okay. Next, so 1 metric HP to 0.735 kilowatt. The metric HP generated is given by metric HP, that's normally is equal to 9.81 eta QH by 0.735, that is nothing but 13.33 eta QH. Once again I am saying Q is nothing but the discharge and H is nothing but the height of fall. Next, gross head, operating head and effective head. Let's see all these three. What is maybe gross head, operating head and effective head. Gross head is the difference in the elevation of the point of diversion of water for a hydel scheme and the point of return of water back to the stream. Operating head is the simultaneous difference between elevation of water surface in the forebay and the tail raise after making the due allowance for approach the exit velocity head. The effective or net head is the head applied to the turbine and difference of head at the point of entry and exit of the turbine, taking into account both the velocity and pressure heads, primary of continuous power heads or secondary power. The primary or firm power is that or firm power. The difference of the head, the primary fin is that for carrying the load of the corresponding to the minimum stream flow with the consideration of the pondage and load factor. We should be clear. It is the minimum continuous power available from the power plant under the most adverse hydraulic pressures conditions. Secondary power or surplus power is the power other than primary generated at the plant. The term surplus power is also sometimes used to distinguish the excess power available, particularly at night times, when owing to low or no load continuous. There is no use of the power, installed capacity, dependable capacity. These two topics, installed capacity and dependable capacity, are nothing but the installed capacity of the power station shows the total capacity of all the turbine generator units installed in the power station. Dependable capacity is neither but is the load carrying ability of the power station with respect to the characteristic of the load to supplied during a specific time interval and the period, and is determined by the power factor, capacity and the load of a station. Okay, now it's time for talking about the load factor, utilization factor and capacity factor, where the load factor is defined as the ratio of the average load over a certain period to the peak load occurring during the same period. And next, that is maintained by the formula of load factor, that is equal to average load over a certain period to peak load occurring during the same period. Certain period by same period peak load. If the average chosen, if the period is chosen in one day, the load factor is known as the daily load factor. The annual load factor of a power station is the annual load factor for the entire area served by the power supplied from this power station. Yes, the load factor for industrial area will be higher than the domestic area, since the power demand by the industry's consumption is more than the domestic area. The utilization factor. Next, coming to utilization factor of our next topic is the ratio of water actually utilized by the power to that available in the river. These latter being limited as shown by the flow duration curve and the discharge capacity of the wheels. With constant head, utilization factor would be also be the ratio of power utilized to that available. Capacity factor or plant use factor or plant factor is the ratio, the average output of the plant capacity. The plant capacity factor is the average load output, average lead by 1.1. Is 1.1 is the installed capacity under peak load. If we take reverse capacity, thinking once about the reverse capacity as 10% of the peak load. If the average capacity is 0, then the load factor on the particular day is equal to capacity factor for the same day. Next, this capacity factor will be identical with load factor with the minimum just equals the plant capacity. The capacity factor for hydroelectric plant commonly varies from about 0.25 to 0.75 depending on load factor, etc. The capacity factors does not exceed more than 0.75 for the usual plant capacity unless in addition to high load factor and complete pondage at the point or plant. A large degree of regulation by storage is made possible. Okay. Now let's see some examples for this so that we get some clear idea on what are the main things that we have learned right now, and we just put into the application for making it clear. In example 251.1, let's see what the question they have mentioned. Three turbo generators, each of capacity 10,000 kilowatt, have been installed at a idle power station during a certain period of load. The load on the plant varies from 1000 to 12,000 kilowatt to 26,000 kilowatt. Okay. Calculate first one total installed capacity, next load factor, next plant factor, and they are asking us to calculate all this. Okay. Total installed capacity is 3. 3 into the capacity generated is 10,000 kilowatt is totally 30,000 kilowatt. For load factor, we have a formula average load by peak load. Average load is nothing but by 2. That's nothing but half into 12,000 plus 26,000. That's nothing but 19,000 kilowatt. Okay, fine. Peak load is nothing but 26,000 as they have said. Okay. Next load factor would be like average load by peak load, making the same 19,000 by 26,000, we get approximately 93.1 percentage. Great. Next, they are asking us to calculate plant factor. Next to load factor, plant factor. That's nothing but energy actually produced by maximum energy which can be produced. Okay, the question is clear. Now taking into account the same, taking energy actually produced in hours is nothing but half into 12,000 plus 26,000 into T, where T is nothing but time. The maximum energy that can be produced that would be like 30,000 into T. We get 63.3 percentage approximately for plant factor. Okay. Next, they are asking us to calculate the utilization factor. Utilization factor, we have the formula directly power, maximum power developed by total power that can be developed. Okay. There is difference between plant factor and utilization factor. Plant factor is based upon energy and utilization factor is based upon power. It is directly 26,000 by 30,000. We get approximately 7.86.7 percentage. Okay. Next, now let's run off to next example. A run-off river hydroelectric power station is proposed across a river at a site where a net head of 30 meters is available on the turbine. The river carries a sustained minimum flow of 40 cumsecs in dry weather, and behind the power station, sufficient pondage is provided to supply daily peak load of demand with a load factor of 73%, assuming the plant efficiency of 60%, determining the maximum generating capacity of the generator to be installed at the powerhouse. If the daily load pattern 20 hours average load and 4 hours peak load, determine the pondage to be provided to supply the daily demand. Okay, let's see. They are asking us if daily load pattern indicates 20 hours, they are asking us to provide supply the daily demand. The average electric energy is given by P is equal to 9.81 QH theta. That is equal to, finally we are getting 20.7063.2 kilowatts. We have the load factor, direct formula average load by peak load, where peak load is nothing but average load by load factor. Eventually same. On making the calculation simplified, we are getting 7063.2 divided by 0.73. Obviously, it is 9675.6 kilowatt. Peak load is guaranteed. Next, maximum capacity of generators to be installed is installed for getting 9675.6 kilowatts. Okay, they made it clear. During 3 hours of peak load, the excess power to be developed from the pondage is, we have to minus this from the above one. So we get 22,612.4 kilowatts. Okay, that is clear. The discharge required for developing the above excess power is, so we have to make use of the content what we got earlier right now. Where discharge is equal to P by 9.81 H eta. Where now we are going to calculate the discharge on applying all equations and notations that we have got simplified calculated. We get the discharge of approximately is equal to 14.8 cubic meter per seconds. Now pondage area would be into 4 into 3600. Discharge into 4 into 3600, that is 21.3 10 to the power 4 meter cube. Meter cube we mentioned because it's a volume pondage required. Okay. Here come to the end of the last example that we are going to see. A runoff plant has an installed capacity of 15,000 kilowatt and operates a 30,000 load factor. When it serves as peak load station, what should be the plant efficiency? May be taken as 82% when working under a head of 25 meter. Also calculate the maximum load factor of the plant when the discharge in the stream is 32 meter cube per second. Solution, let's see what was the solution they have clearly made for that. The average power developed when the plant operates as peak load point with a load factor of 30%. So it is directly 15,000 point into 0.3, that's nothing but 4,500 kilowatts. Now the discharge that is generated for the above power is P divided by 9.81 H eta. That's nothing but P, we know the value 4,500, and H and is nothing but high, that's 25, and eta is nothing but 0.82 efficiency. We are getting totally the discharge is 22.38 meter cube per second. If the stream has a flow of 32 meter cube per second, power developed is right now we have to, there is somewhat lesser than that. Power is equal to 9.81 into 32 into 25 into 0.82. Is finally power generated developed is 66,435.36 kilowatt. The maximum load factor that can be is the value we got for power divided by 15,000, that is approximately 42.9%. Fine. Hope you all understood the example sums that are related to the content we have seen earlier. If you have any queries, please let me know, and thanks for watching everyone.